The basic structure of almost bipotential amplifiers is as the same. But main differences between biopotential amplifiers are due to these following factors. The first one is the signal spectrum or bandwidth required for the recording. And the second one is the signal amplitude. As you can see, various bipotential signals, for example, EOG, has a signal spectrum limited to 10 Hz, and also EOG signals consist of DC potential signals. The voltage amplitude is low, also lower than EEG, ECG, EMG, and other types of the signals. The bandwidth of EEG consists of higher frequency and also higher amplitude. The ECG's bandwidth is more than two previous signals, and also the voltage amplitude is higher than before, higher than two previous one. EMG also has high voltage amplitude and also consists of high frequencies in its bandwidth, and AAP also has high voltage amplitude and high maximum frequency content. This plot is required, is necessary to design a good amplifier. We don't have any amplifier. We don't have an amplifier to record all types of the signals. We should change the structure. We should change the filtering circuit. We should change the gain of a circuit. For example, if you want to record EEG, the maximum amplitude of 1 millisecond, maximum. But as you can see, typical voltage amplitude is this. Therefore, if you want to reach to 1 voltage, you need to have an amplifier with a gain of 10,000. But as you can see, ECG's voltage amplitude is something like this, and only thousand of gain is enough to reach to 1 voltage at output. Therefore, you should be aware about the frequency and voltage content of your signal to design design an appropriate circuit for your signal recording. In these slides, in these next slides, we will talk about some specifications of some important signals, bioelectric signals, and we will start from electromyogram and related amplifiers. We need a frequency band from 25 Hz to several kilohertz, and also signal amplitude range from 100 microvolt to 90 millivolt. We have wider frequency response than ECG amplifier, and these amplifiers do not have to cover so low a frequency range as the ECGs. Motion artifact problems in this signal because of the movement of the body is important, but because of the minimum required frequency, we can remove all the motion artifact using a low pass filter, a high pass filter, because the motion artifacts frequency content is below 10 Hz, and using a high pass frequency will remove all these bad motion artifacts. In a skin surface electrode recording, the levels of signals are generally low because we are recording out of the body, 1/10 to 1 millivolt, and this leads to higher gain requirement. Electrode impedance is relatively low, ranging from about 200 to 5,000 ohm, because we use usually large area, some electrodes with large area. But in needle electrode recording means that we record signals inside our muscles, and the EMG signals can be an order of magnitude stronger, thus requiring an order of magnitude less gain. We need less gain than skin surface recording. And furthermore, the surface area of the EMG needle electrode is much less than that of the surface electrode. So its source impedance is higher, therefore a higher amplifier input impedance is desirable for quality signal reproduction. The area of the electrode is small, therefore we need an amplifier with higher input impedance to be compatible with the high input impedance in our source. Amplifiers for use with glass micropipette, intracellular electrodes, and related amplifier specification are discussed in this slide. Intracellular electrodes or microelectrodes that can measure the potential across the cell membrane generally detect potential on the order of 50 to 100 millivolt. Generally, this range is the highest range among all the bioelectric signals, and therefore we should consider this high voltage, and we will need less gain in our amplifiers. Their small size and a small effective surface contact in intracellular electrodes give them a very high source impedance. These features place on the amplifier the constraint of requiring an extremely high input impedance. For example, 1 giga-ohm as input impedance of our amplifier. Furthermore, the high shunting capacitance of the electrode itself affects the frequency response characteristic of the system. And often positive feedback shims are used in the potential amplifier to provide an effective negative capacitance that can compensate for the high shunt capacitance of the source. The frequency band of this recording is from DC to 10 kilohertz. It means that we have a wide range of frequency content, and we should consider this wide range. A pre-amplifier circuit that is especially useful with microelectrode is the negative input capacitance, utilizing a positive feedback shim, as I told you before. Please find this page from the book, and this is S in this figure. You can correct it. Find this figure and read the related and following descriptions and also equations about the finding the correct feedback capacitance, positive feedback, to generate a negative capacitance to remove the capacitive performance of the micropipette electrodes. Read it. Maybe one of your questions in the exam is from this page and related descriptions. Electrocardiograph requirements will be discussed in this slide. As you can read, the EEG requires an amplifier with a frequency response of from 1/10 to 100 Hz. Surface electrode, as in clinical EEG, when you go to a physician in clinical position, they will use surface electrode. And in this situation, amplitudes of signals range from 25 to 100 microvolt. Thus, amplifiers with relatively high gain are required. These electrodes are smaller than those used for ECG, so they have somewhat higher source impedances compared to ECG. And a high input impedance is essential in EEG amplifier because the signal levels are so small. Common mode voltage can have more serious effects. Therefore, more stringent efforts must be made to reduce common mode interference as well as to use amplifiers with high CMRR and low noise. We have two main parts in a complete amplifier circuit. The first part is pre-amplifier and the second part is the main amplifier part. Pre-amplifiers must have low noise. First of all, low noise is important. Have high input impedance to overcome the high source impedance, and coupled directly with electrodes, minimize charging effects on coupling capacitors, and also deal with offset voltage. Thus, it must have low gain, and for safety reasons, the preamplifier is electrically isolated from the remaining amplifier stage. In brief, we can conclude that the preamplifiers are not for amplify, because we should overcome some challenge like noise, like input impedance, connection to the electrodes, charging effects on coupling capacitors, and also offset voltage. Therefore, the main purpose of designing a preamplifier is not the gain. And also, safety is important in preamplifiers. Electrical safety is an important issue we should consider in designing preamplifiers. In this figure, a general and simple ECG amplifier with a gain of 25 in the DC coupled stage and 32 gain at the main amplification part, and the total gain is 800, and also the frequency response of this system is between 0.05 to 106 Hertz, and the flat region of the response is from 4 to 14 Hertz. This is a general and feasible design for you to use it in the lab to have a good ECG amplifier in the laboratory situation, not in the practical clinical situation. Read it in detail, check the parts, try to calculate the gains generated by each op-amps, and in abstract, read the description related to this figure. And also you can read this text related to that figure. We have talked about some details, about some numbers, some values of some parameters, some resistance, and some adjustment of parameters. Also have been considered in this slide. Especially you should focus on the restoration time and these parts, these values of parameters are important in this figure.